Let me double check. Yes, we are. Okay, so David's talk today is on Geo Energy Observatories, characterizing the surface to support the transition to a low carbon economy. And for those of you that don't know David, he is a trained engineering geologist with an MSc from Leeds and a fellow of the Geological Society with 15 years experience of applied geology research and consultancy across the UK and overseas. He's a science lead for the Cardiff Urban Geo Observatory and researches the geothermal resource potential of the UK landmass to support decarbonization of heat and power. You might also find him mapping geology and geohazards in far-flung places or paddling out at your local surf break. So we are going to be, as usual, going to be recording the talk. And if you don't already have your phones or computers on mute, can we do that, please, before the talk? Thank you. Over to you, David.
Thank you, Bridget. I'll just put my phone on mute.
I'll do the same.
And yeah, shame I can't put my children on mute, really, isn't it? No, I shouldn't say that on a recorded thing. Yeah, shall I share my screen now?
Yes, please.
Okay. Hopefully you can see the slide.
Yes.
Yeah.
Yeah.
Great. Okay. So it's a great pleasure to be asked to join the Thames Valley Regional Group tonight. And shame I can't be there in person to see you all and share a cup of tea or a beer, but at least we can do Zoom for now. It's a pleasure also to see Bridget again, because I was very interested in her MSc work in South Wales on landslides, and it's great to see her and Victoria and some of the others in the room. So the talk content, I really want to cover three main topics in the talk outline that was on the website. I must say, yeah, I was asked to do this talk by my colleague Gareth Farr, because he has been working with me for many years, over 5 years. Sort of, we set up and started this Cardiff Urban Geo Observatory idea, and but he's recently moved on to the Coal Authority, so we wish him well. And he suggested that I do this talk on his behalf, so I was very happy to pick that up for him. So hopefully I'll do as good a job as he would. So if you have any questions about the Coal Authority and heat and geothermal heat from mines, you can ask Gareth Farr. Yeah, so what I wanted to kind of cover first is the context of decarbonisation in the UK, the role of Geo Energy Observatories, and explain what they are. And I want to particularly draw on the geothermal research aspects of them, partly because it's kind of what I'm interested in, and we haven't got time to talk about all of them and everything you could do at them. So I'm actually going to focus on the Cardiff Geo Observatory in particular, which is one of 3 geo observatories in the UK. I'm not going to really talk about Cheshire or Glasgow geo observatories, but I will just say you could have future talks about those facilities, the research facilities, if you are interested, and you can look on the UK Geos website as well to learn more about those, and if you want to use those for research yourselves. So just before we crack on, I want to just outline something important. Geothermal energy, it means a lot of different things to different people, and it's been in the news a bit here and there. It's gaining traction as a kind of decarbonisation technology for the UK. Geothermal energy is very well established across the world in places like Italy, New Zealand, Iceland, where they have you know, hot kind of volcanic systems under the surface, and obviously they drill some holes and get very hot water out and use it to make electricity and heat buildings and things. We don't have any active volcanoes in the UK, fortunately, or unfortunately for geologists, because they're fun to research. But what we do have is what we might call kind of two main groups of types of geothermal energy. So the first is what I would call shallow geothermal energy, which is often called ground source heating and cooling. It's the same thing really. And there's three different main types of that. There's open loop ground source heat pumps or groundwater source heat pumps, which I'll touch on tonight quite a bit, because that's the main opportunity in Cardiff and in the chalk. There's also closed loop geothermal arrays where you don't abstract groundwater, you actually circulate cold fluid in pipes in the ground called borehole heat exchangers. And you combine that with a device called a heat pump, which raises the temperature up from maybe 13 degrees to 40 or 50 or 60. And some heat pumps even can go as hot as 180 degrees now, very high temperature ones, and to heat mainly buildings, but also for some industrial processes and greenhouses and things. And then there's another form of which open loops really system, which is called mine water energy. So as you will all appreciate, there are abandoned coal mines across the UK landmass, typically between, well, 0 and about 1,000 meters deep. And there's an opportunity there. Where the water's quite deep, it might be quite warm in places, sort of 15 to 20 degrees, maybe even 25 degrees. Again, you can basically pump out the water. You can drill into a mine shaft or a mine roadway, drill out, suck out the water, pass it through a heat exchanger, and again, use that to use heat pumps to heat buildings. So there's lots of activity and interest going on in this area at the moment because for reasons we'll come on to. The second type is what we call deep geothermal energy, which is probably what most people think of when they think about geothermal energy. And the two main systems here are hydrothermal systems, where basically you drill a hole maybe 2, 3, 4 kilometers down into typically a deep aquifer like the Sherwood sandstone or the Carboniferous limestone, to take some UK examples of targets. And you essentially suck out the water from depth, which might be 50, 60 degrees C, and you can inject it back in at a higher level, and it will then warm up and sort of recirculate the water. That's called, you can use that heat. It's hot enough to use kind of directly. You don't have to use a heat pump so to heat that water up. And then the other type is a petrothermal system, which is even deeper, and some people call these engineered geological systems. And this is where in places like Cornwall, where you've got granites under the subsurface, there's a lot of radiogenic breakdown of the minerals in granite, so that produces heat. It's not still hot from when it was a volcano. That's a kind of misconception a lot of people have. It's basically the radionuclides in there that drive a lot of the heat, and there's quite a lot of high heat flow because there's a lot of quartz, and the heat can get from the core of the earth out up through that quite quickly. So you tend to, if you drill down maybe 5 kilometers, 6 kilometers in the UK and hit one of these granite bodies, for example, you can hit maybe 100 degrees, 150 degree temperature, and you can basically put down hot water, inject water, it heats up. You might need to form some cracks in it, or if you hit a fault or a fracture zone, that's quite good because you do need some permeability, some flow. And then basically hot water will come back out, and that's hot enough to actually generate electricity. So that's as well as heat for buildings. So that's the only really way that we're generating electricity from geothermal systems at the moment in the UK. So hopefully that's just got that clear in people's minds. The role of geothermal heating, well, the role of geology in decarbonisation. I quite like these Chinese proverbs. One is dig the well before you're thirsty. I mean, you know, basically we've got a problem coming down the line here with rising levels of carbon dioxide in the atmosphere. That's causing melting of ice caps, climate change, more intense climate fluctuations, which is, you know, going to drive global mass migration. It's going to cause forest fires. We're already seeing lots of problems. It's well documented. So, you know, in the UK context, we need to cut the amount of carbon dioxide that we're all emitting and that our industries and buildings are emitting. to meet our net zero targets, which we all know about. So one way you can do that, as I mentioned, is geothermal heat pumps. They are a proven way to efficiently provide heating and cooling to buildings. They're very popular in Scandinavian countries and in the US. They're less popular in the UK, but it might surprise you to know that there are about 35,000 ground source heat pumps in the UK that we know about, and there's probably a lot more that we don't know about because for reasons I'll come on to, which Victoria probably has some interesting opinions about maybe. So heat pumps they're good because they run on renewable electricity. If the electricity is renewable, you're not producing any carbon dioxide, and you can basically heat up water for buildings in a very energy efficient way, and they're very clean, and you don't get carbon dioxide in the air, and there's no risk of carbon monoxide poisoning from gas that you might have from, say, a gas boiler. But there's different ways to deploy them. You can use air source heat pumps, or you can use ground source heat pumps. Obviously, I'm talking about ground source heat pumps today as a kind of technology to take us through to net zero, a potential technology. It's not the only one. But to design good systems does require some geologist input and some hydrogeologist input. So, you need to know you're drilling boreholes in the ground to try and extract heat or inject heat to store it maybe interseasonally. You need to know about the geology. You need to know about the ground conditions. You need to know about the groundwater situation. If there's artesian water, can be a risk for drilling. It's useful to know the ground temperatures because they do actually vary a bit across the UK. Particularly in the top 200 meters, where typically we're installing these type of sort of shallow geothermal boreholes in the UK. We need to know about if they're going to have an impact on the geotechnics of buildings and infrastructure around them. It's good to know about the thermal properties of the soils and rocks, because that's important for designing and sizing correctly these borehole heat exchangers. And maybe we will want to know about, of course, drilling hazards like karst, pingus, mines, and there's lots of other things, isn't there, that we could running sands. So lots of other kind of geohazards that we might come across, as with any drilling or piling project. And we can also use energy piles to actually extract energy for buildings as well, and that's kind of quite commonly done as well. But of course, with more buried infrastructure comes competition for underground space. If you drilled lots of boreholes in a city, the picture on the right is an example of some buildings, kind of Google Earth type image, but basically the buildings are colored up for their heat demand, and the heat demand is how much heating in kilowatt hours per year is required to heat or cool that building. So depending on the building age and type and use, it will have a different heating demand. Sorry, I've just had something come up on my screen that I just need to close. I will just carry on. Yeah, so, but there are some challenges for sustainable management of this use of heat in the subsurface. So a colleague of mine, Corinna Bessier from BGS, and some other colleagues recently wrote a sort of science briefing paper on this question of who owns geothermal heat, because in the UK, there's no legal definition of heat or subsurface heat. So, and therefore we can't regulate it. We can regulate water, but we can't, water is a heat carrier fluid, but we don't regulate heat because we can't legally define it yet. So in order to regulate heat, we would certainly need resource estimations, just as we do for water resources, legal definition of heat, predictive models on how heat flows and in the subsurface and might interact with schemes and buried infrastructure, controlled waters, aquatic habitats. And we're basically calling for some joined up regulation in closed and open loop ground source heating. Currently open loop ground source heat pumps that abstract heat directly through the water abstracted from an aquifer are regulated by the environmental regulator through the permitting and abstraction licenses. There is no regulation of where closed loop systems go in the UK currently. except one exception that I know of. One way to answer some of these challenges is by establishing geo-observatories to basically do research on how heat flows in the subsurface to generate some evidence for how we should best perhaps regulate heat in the future and develop policy around this. I must say, I think London has led the way in establishing a register of ground source heat pump heating and cooling systems, which I think was very much led by Victoria and her colleagues. And this actually inspired us to do the same in Cardiff. So we're now currently, and actually nationally, so now BGS is working with an organization called MCS, who essentially provides some sort of consumer, some best practice guidance for installations of ground source heat pumps to make sure that they're installed well to a certain standard. We're working with them to build a national register of geothermal wells to aid planning and avoid basically infrastructure strikes. So if someone's building a tunnel or a microbore or something in the subsurface, you know, you don't want them like running into someone's geothermal system. And unless we know where they all are, you have no way of not damaging their infrastructure. So we're kind of pushing this idea a bit at the moment, and we're hoping to get some sort of website layer on our GeoIndex, so you can actually see where we know that where there's some geothermal boreholes when you're doing your desk studies. But that is not finished work yet. I'm just giving you a little a teaser there. Hopefully in the next year or two it will be. So at the BGS, we are obviously interested in geothermal research because it involves the geology of the UK, and decarbonisation is one of our kind of three main challenges that BGS are kind of focusing on at the moment. So as I mentioned, we would define that as sort of any shallow geothermal systems, anything in the top 400 meters, really. Most of them are 100 to 200 meters, but they're getting deeper and deeper as drilling technology develops. I talked about deep geothermal energy. So we're interested in resource energy storage potential. So you can, as well as taking heat out of the ground, you could use it to store waste heat from an incinerator or some industrial process. And then you could use that heat to heat buildings, maybe through district heating systems, district heat networks, when the heat is most required during the winter time. You could store summer heat using solar panels to collect the heat, and then store that heat via boreholes in the ground in the summer, and then take that heat back out in the winter to boost your heat supplies in a very efficient way. We're also interested in the kind of microbiological effects in the subsurface and water quality in aquifers of the use of kind of geothermal systems. They were interested in the thermal and mineralogical properties analysis of UK rocks and soils, so we can test cores and things and make geothermal potential maps with those. Some of the work we're doing at the moment. We have established this network of experimental field research sites called UK Geos, and say there are 3 sites: Glasgow, which is focusing on potential of coal mine heat; Cheshire, which is looking at the Sherwood Sandstone aquifer mainly, and opportunities for geoenergy sort of uses of that, including aquifer thermal energy storage, as well as CCS and other types of energy storage technologies that could be potentially experimented on in an array of boreholes, which are going to be built there next year and be open to UK researchers and overseas researchers to come and run experiments in those kind of test boreholes. And there's more on the UK Geos website. If you Google UK Geos, you'll find a nice shiny website that's got lots of open data and reports and things. And we're involved with various international research networks on shallow geothermal energy, including the IEA, some collaborations with other geological surveys across Europe in the Muse project, and cost actions, which are sort of research networks. Again, kind of very much kind of European research networks, and the Brit Geothermal project, which looks at kind of, I think it has annual meetings on kind of British geothermal energy research. So if you're more interested in British geothermal energy and what's going on, you can search out Brit Geothermal as well and go to the GeoSoc meetings that they co-host with Brit Geothermal. So yeah, why do we need geo-observatories? What are they? So this is the kind of text on the website. It's a bit heavy, but essentially, you know, I think I've kind of outlined already really that if we are to develop safe alternative energy technologies, we need to understand how they're going to impact with the environment, particularly when they're deployed at scale, particularly in urban areas or where there's sort of sensitive assets or aquifers or habitats. So part of perhaps those answers will come from a network of observatories, which is basically a way of saying we monitor the loads, we monitor the geology at a sort of large site, campus scale to city scale, to understand some of the processes going on in the subsurface in terms of water movement and heat movement and the impacts of using the subsurface on those environments. And that data and information can feed back to government and support regulators in developing policy and sustainable sort of policy, you know, ultimately to deliver a clean economic growth for the UK and decarbonisation. The facilities in Glasgow and Cheshire are publicly run by BGS, UK Research and Innovation, UKRI, or UCRI as some people call it. But the Cardiff Observatory is really just a BGS collaboration with Cardiff Council and hasn't been funded by this Geo Observatories project. So it's kind of a sister project to these Cheshire and Glasgow ones. So now I'm going to talk about the Cardiff Geo Observatory as an example of how we can use geo observatories to explore urban geology and what it can do for us in terms of kind of a sense of what the urban geology is under our cities where most people live, ecosystem services, and how it can help us decarbonise. So Cardiff is in South Wales, as many of you will appreciate. BGS has an office in Cardiff. It's you know, see the place where Welsh government sit. So it's quite an interesting place for us to have a look at the urban geology and actually start to sort of dig beneath the surface a bit and see what's going on under a city. Because often as geologists, you know, we like going out and looking at mountain outcrops where there's lovely exposure of folds and things, but the reality is most of us live in cities, and most of our cities are built on sloppy, wet, muddy sediments in the UK, on coastal areas, a lot of them, and actually you can't really access the bedrock geology very well, and you've got to be quite interested in Quaternary geology because there's usually spreads of glacial or Quaternary geology on the bedrock, and that's actually a lot of the material we're dealing with in terms of infrastructure projects. So this is a picture of Cardiff looking from the Bristol Channel kind of northwards. The big area of water there is called the Cardiff Bay, and there's a barrage here, which is basically an artificial kind of barrage that created a freshwater lagoon, and it was built in about 1996. The reason being that Cardiff is an extra kind of industrial city. It had a lot of docks, a lot of coal. I mean, at one time this place had it was the world's largest coal exporter, because the coal would be brought down from the South Wales coalfield valleys on trains, loaded onto ships and shipped out all around the world for coking and steam coal. But now that industry's all gone, and the city wanted to regenerate this kind of dock area, and so it generated part of that regeneration effort was to build an inland waterway which people would want to kind of live by. So that's Cardiff Bay. It's got a population of about 300,000 people. So yeah, in about 2014, BGS decided to spend some of its money doing some urban geology field investigations in Cardiff. So we were the reason we were interested in it is because the council told us that they were particularly interested in fuel poverty, and they were trying to figure out how they were going to make heating cheaper for people and more secure in the future. And then we sort of clocked on to the fact that no one really uses these heat pump devices, and they could be. And then we clocked onto the fact that there was actually a body of groundwater under the city that could be used to supply heat pumps with heat. And no one was using it, and no one else was using the groundwater for anything else anymore, because there's not many industrial activities using groundwater in Cardiff. So it's got this shallow unconsolidated gravel aquifer, glacial gravel aquifer, sort of sheet deposit. So we started doing some borehole monitoring. We started measuring some of the soil properties and rock properties, working out where the best borehole records were and that kind of thing. We didn't have much money, so we had to do what we could on the cheap, really, and that actually meant collaborating. So it turned out the council have, quite incredibly, a borehole network of about they had at the time about 200 boreholes across the city. And as I mentioned, when they built this barrage, the water level in that bay, as that bay filled up, that lagoon filled up, the groundwater table level rose, or there was a concern that the groundwater table level would rise behind it, and the houses that were built, the Victorian terraces that were built, just in the behind it, the basements might flood. So there's this concern. So as part of the Cardiff Bay Barrage Act, the council set up a team to monitor the groundwater levels, just levels really, but they did some chemistry as well, from about 1997 onwards, and they've been monitoring it till 2019, when they no longer had to monitor it by law anymore. We essentially teamed up with them and used their boreholes to do temperature monitoring of the groundwater, which there's a photo of my colleague Ashley Patton and Gareth Farr on the right, sort of using a conductivity temperature level dipper to go down around the city and monitor all these old wells. We also, we monitored some industrial site wells, as well as the council's ones. So we found any well that was possibly open and went and dug it out and found the manhole covers and collected data every meter down the water column. We collected a temperature measurement at every meter. So we end up with a load of temperature profiles and conductivity profiles and water level measurements. From that, in GIS, we produce these temperature maps, which show you the kind of the groundwater temperature at a shallow depth, the type of depth that you could use to abstract the water for a very shallow kind of open loop ground source heating type system. There aren't any in the city at this point. So what's quite interesting is it surprised us how warm it was down there. We expected the typical groundwater temperatures in the UK are about 10 degrees. So when we were getting temperatures of 14.8 degrees and typically 12.3 degrees average, 13 degrees kind of average across the city, from the area that we were monitoring, we were kind of surprised, because and then of course we realized it was actually the urban heat island effect. And so all the heat that's generated in a city is also, some of it is conducting into the ground, through people's basements, through tunnels, electric cables, and even just the air being slightly warmer in a city. Some of that, basically the ground warms up underneath you. And we see this in London. I think the ground temperatures in London are up to 5 degrees higher in central London than they are perhaps out in the sticks, because of this urban heat island effect. So that's actually a potential bonus for kind of geothermal heating schemes, where the warmer the temperature is of the water that you're extracting for a heat pump, the better it will run, the better efficiency you'll get from a heat pump. So that's quite an interesting prospect. We then developed a 3D geological model of the city's Quaternary geology to get to basically so we can map out this shallow gravel aquifer, try and see how thick it was, because in part it's buried, it's confined under tidal flat deposits, which are the yellow color, and all the dots are the boreholes that we were monitoring. And there's also there's glacial till, and the bedrock's mostly Triassic Mercian mudstone under Cardiff. So this model is kind of the start of understanding the subsurface distribution of the Quaternary deposits, with a particular interest in mapping out this aquifer body. But of course, that geological model, which is useful for other things too. So it should be useful for construction. It should be useful for people doing desk studies in the city for projects. It will be useful for flooding models, geohazard mitigation. Could be useful for all sorts of things. So as well as that, we then in 2016, we established, we got some money from Innovate UK, and we actually installed a pilot open loop ground source heat pump system, the type I was talking about, where you abstract water, and there's a picture of it on the left hand side. You extract water from, we're just extracting from 15 meters below ground level in a shallow borehole, shallow well. And that basically, that water comes out at 13 degrees C and goes through a heat exchanger and a heat pump, which raises that to 45 degrees, heats a school, and re-injects the water at about 10 degrees back into the aquifer in another a recharge borehole. So essentially, we installed that, it's heating a school, and we've been monitoring how well it works and what the impact on the aquifer has been for the last 6 years, which has taught us some things about whether or not that technology is technically viable in that type of thin aquifer. And it does seem to be at that scale. Say we also developed, my colleague Johanna Schagdegger developed a groundwater model and a groundwater balance model. So again, what we wanted to do was understand the flow of water through that gravel aquifer in order to understand what the kind of recharge was, what the impact from sewer leakage is into the aquifer. And then we want to, we're doing that because in the future, if we ever, well, the next step will be to sort of try and convert that groundwater flow model into a heat flow model for the city in a way that can help the council and maybe the regulator decide where heat pumps systems like this can go and what impact they would have on other adjacent systems because of the heat plumes that they produce in the subsurface. So this is kind of building that knowledge base to hopefully answer some of those more complex sort of regulatory planning type questions in the future, and as a bit of an example of how you could do that. I mentioned the heat island effect before. So as I say, we see it in London, we've shown you can see it in Cardiff, and the plot on the right is some brand new data that I'm treating you to, which is basically some temperature plots of groundwater temperatures in different parts of the UK. So the black one is Cardiff, and you can see that we measured 11 degrees rising up to about 13 at around 200 meters depth. I thought you'd be interested in, oh sorry, the black one is actually Colchester, so that's in the chalk. So I thought you'd be interested in that because that's near you. That's a new ground source heat pumps, large system going in Colchester to supply 300 new build houses with groundwater as their main heating source. So that's a really interesting project. So we did do a bit of baseline monitoring there just to bring the southeast into it. And then the other ones are from the Cardiff, so the dotted one, and there's two from Cardiff actually showing that even in the same city about 3 kilometers away, the ground temperatures do seem to be slightly different, and we're not quite sure why. It may be the instruments you used to measure it, or it may be that there is actually stuff going on, like some leakage from some industrial source down into the bedrock, or into the aquifer, or maybe there is even faults in Cardiff with a thermal spring up at, that's 20 degrees up at Taswell. So there could even be leakage through kind of faults in the bedrock that are concealed by the superficial. So yeah, lots of open questions. And the other blue one is from Glasgow at the Geos site where we're using fiber optics to monitor the temperature. So what's quite striking actually was that Colchester's the coldest one, which surprised me because it's quite far south. Growing up in East Anglia, I appreciate the quite balmy temperatures. But it's quite interesting how that's the coldest in the chalk, and but it is a bit warmer than some of the chalk in London, where obviously you've had the impact of, sorry, it's cooler than some of the areas in London where you've had impact from overheating in the chalk. Yeah, and in Glasgow, surprisingly warm, really, because again, it's very far north. You'd expect it to be the coldest geothermal profile, but it may be because of the coal mines there that it's a bit warmer. And I say in Cardiff, it's actually the warmest, so it's quite a marine climate with these other kind of urban heat island effects. So it shows there is a bit of variation in ground temperatures in the UK. So the configuration of this open loop heat pump is essentially, there were 2 shallow boreholes drilled. Here's a cross section of the geology. As I mentioned, the geology in Cardiff is generally Triassic Mersey mudstone bedrock, followed by about 8 meters of sand and gravel aquifer, but it's a glacial sand and gravel, glacial fluvial deposit. I'll show you a picture of it in a minute. And then there's tidal flat deposits, which are soft, silty clays, mostly organic clays. The groundwater table is about, it's a shallow water table at about 3.5 to 4.5 meters below surface. It's quite shallow, and then there's layers of made ground. So we're extracting water from this target aquifer from about 15 meters down, pump it out, 0.5 litre per second. That goes through a heat pump device, which is about the size of a small fridge. That heat then goes off into the building and heats that, and the waste water, which gets re-injected at 11 degrees C back into another borehole, which is only 20 meters away. Now this 20 meter separation is not ideal, because ideally you should have them at least 50 meters spaced apart. Otherwise they kind of recirculate water between the injection and abstraction well. So, but we did that because the land space problem in an urban area where you just literally don't have a big enough kind of garden to separate them that far when you're just dealing with one property's space. So this is kind of an issue. So it's kind of an interesting test of doing something where you knew it wasn't really the best thing to do. And NRW were happy for us to do it as an experiment, but we showed that, we proved that basically that is too close to have these boreholes, really. And the system still works quite well, actually, but it's just not optimal spacing. 50 meters or 100 meters or more is better, depending on the geology, though. We have a series of observation wells kind of nearby, 150 to 100 meters away, so we can sort of monitor what's happening in terms of the thermal plumes being generated in the aquifer. So we're quite interested in that. This is what it looked like installing it. So you got to drill 2 wells. They used shell and auger because it was soft mixed ground. 2 boreholes 20 meters deep. They had to use UXO clearance because it's Cardiff and there were bombs dropped there during the war. The temperatures were 13 degrees below 10 meters all year round, which makes it a very stable source of heat to start a heat pump doing its thing. We monitor the groundwater levels and temperatures all year round for 6 years, every 15 minutes. We've got a big data set now for these boreholes and all the other ones in the city. And we've got a weather station on site. My colleague Ashley made a lovely educational video about the project on YouTube. It's on the BGS YouTube channel. And the photo here shows what these glacial sand and gravel deposits are like. Or the fines are probably washed out a bit, but it's quite a cobbly gravel, essentially. So yeah, that's the aquifer material really that we're dealing with. So it's going to have quite high permeability and porosity. So we monitored the temperature in the aquifer around this heat pump scheme for several years. Here's some data from that, and really it's quite a busy graph, but what I kind of wanted to show was, because we're extracting water and re-injecting it into the aquifer a couple of degrees cooler than the temperature that we took it out, took it out to 13, which is the top red line, and the bottom line is the injection temperature 20 meters away. which you can see is a lot colder. It's typically 2 degrees colder because that's how much heat we remove from it, and we pass that to the heat exchanger to do its thing, and the heat pump to do its thing and make it 50 degrees using a gas compression cycle. It's magic, really. But you can see over the several years, what you'll notice is the temperature in that production well, the abstraction well, is dropping a bit from 13 down to, didn't drop much in the first year, and then it dropped down to 12.5 and then down to 10. And this was partly because of the way it was set up. So it was kind of dropping faster than we might have expected. But after a few years, you'll find that the temperatures kind of level off as the system kind of stabilizes and reach an equilibrium. But what we did notice, which is quite interesting, when we turned the system off for a year because there was a malfunction, and it basically allowed the aquifer to heat up again. And that was almost like a kind of heat injection experiment, in that the advection of the groundwater basically caused the aquifer to reheat and rejuvenate it, and it nearly went back up to its starting temperature. So it gives you some data on how well heat kind of is passing through the aquifer system by the groundwater flow, and what that means for potential heat storage in the subsurface, and whether that heat would get whisked away very easily if you tried to store heat in that aquifer unit. Yeah, another thing that we've been involved with is working with our European colleagues, and this is a European project called Muse, essentially 16 geological survey partners, all sharing geothermal resource estimation techniques and developing management best practices for shallow geothermal deployment sustainably in urban areas. We had 14 pilot areas, one of which was Cardiff. And from this, there's a website there. There's lots of sort of fact sheets and reports on there. But one of the things I want to show you is this web tool that we produced. So there's a web tool here, which essentially, one thing we wanted to do with this, so each geological survey produces a kind of web tool. So Vienna's got one, Brussels has got one, Bratislava's got one, and there were lots of others, cities, Catalonia. But essentially, some of the 3D model data, like the aquifer thickness data, we've managed to put on this website. So, and the other data layer we put on here is the location of existing shallow geothermal installations, which includes open loop and closed loop systems. So the idea that we were inspired to do this by the work of the EA in London and Thames Valley, because we realized the importance of knowing where the other schemes are, so you can kind of design, so people designing these schemes can know if there's a scheme very close to theirs, because it could have a thermal impact on their scheme. So we are now building up this kind of database of, whenever we hear about a new system going in, there aren't actually many that we know about in Cardiff, it's about 5 or 6, but we'll add it to the database if you like. And actually this is part of a bigger move by BGS to try and develop, similar to our borehole database, a database of existing geothermal wells. And so we'd love to get London and the EA involved, where you have a database and we can add the data we know about. We've got about 30,000 data points from the MCS we can add into there. So yeah, that's kind of one of the, let's say, informatics and data initiatives we're kind of pushing on at the moment as part of sustainable development of this technology. Some of the other things we've done are make kind of geothermal decision support maps. So there's an example here from Cardiff where we've used that 3D geological data and kind of converted it into a bit of an easier way for non-geologists to digest. So in the map, the colored areas show the extent of this gravel aquifer. The yellow, the green areas and dark blue areas are areas where the aquifer is at least 5 meters thick. And that means you could consider using an open loop, shallow open loop heat pump system. It would probably only be big enough to heat a smallish building, not like for a whole district heat network, but so it's got kind of limits on how much heat and water perhaps you could abstract sustainably. But it's the first way to show planners where the good bits are for open loop ground source heating in this bit of geology. The yellow bits show where it's more patchy in thickness and the gravels are more clayey. And so it was probably not as good at Aquifer in terms of the potential for open loop systems. So in those areas, you could say, well, they'd be fine for kind of your more closed loop type geothermal systems, whereas those other zones, the yellow and green areas, the green areas and blue areas would be okay for open loop systems. So that's the kind of thing we can do with geology to help planners kind of better zone where we're going to how we're going to decarbonize using the geology that we've got to best effect. We're getting towards the end now, so particularly resilient energy system design. Yeah, as I mentioned, there's this issue of if we put a lot of these heat pump systems in a small area, there's a chance, particularly when there's groundwater flow, there's a chance they're going to interact with each other thermally underground. It just means that you might not get the source temperature you're expecting if your neighbour's already injecting cold water next door, or maybe you'll get improved efficiency if your neighbour's injecting hot water next door or upstream up gradient because they're using it for cooling. So by kind of interacting with who's using the aquifer and trying to think about how best to locate schemes, you could actually be kind of improving how the optimal use of an aquifer. It does need people to talk to each other, and it needs, the planning and the regulator to get involved. And as I mentioned, the closed loop systems are not regulated. People can put them anywhere, pretty much. So it's hard to know. They will produce some cold plumes, so it's hard to know where this will be happening. But we think it's something that would be quite important to understand going forwards. And ideally, if we're really clever, this is what the Dutch do, of course, is balance the heating load. So what they'll do is make sure that buildings that are injecting heat from cooling buildings and re-injecting heat into the ground, they will inject it into boreholes, which will then be used for heating in the winter. And therefore you're continually like cycling and balancing the heat in the ground. And basically the cooling system will work more efficiently and the heating systems will work more efficiently if you do it that way, because you're just basically transferring heat around between the subsurface and buildings. So some of the tools you should know about, which might help some of you working on these kind of projects. If you don't already know, the Environment Agency and BGS collaborated a few years ago on a project to develop a national, well, it's England and Wales, ground source heat pump screening tool. So essentially, this is a map tool that takes into account some of the geological data and the aquifer characteristics and depths and things. And it basically tells you whether or not a site is likely to be favorable for larger open loop ground source heat pump systems of 100 kilowatts plus. So that might be 5-6 liters per second type pumping rates. Or what we said is at least 1 liter per second pumping rate. Essentially it's based on the 1 to 250,000 scale geology mapping. So it's not really site specific, but it's certainly kind of district specific. So it is worth having a look at that if you are, you are asked to kind of consider the geothermal options in that area and you want to know whether there's an open loop potential. It only really captures the principal aquifers, the bedrock aquifers. It doesn't really capture the type of Quaternary aquifer that I was talking about in Cardiff. So also, look at the Quaternary geology and have a think about the thickness of that. But certainly the bedrock aquifers are going to be the main targets for open loop systems in most of the UK. Of course, if you need more site-specific information, you could get a BGS Geo report to provide a module on groundwater abstraction yields, likely yields, or geothermal rock properties for closed loop systems. There's some more in-depth reading if you really want to. Now I can put these on the slide, or you can go back to have a look at some of these publications if you want to read more about what I've talked about. And I'd really like to thank all the team who have contributed to this Cardiff Geo Observatory project. And ultimately, we hope that this geoscience research will stimulate more urban geology research in the UK, as well as helping to de-risk some of the, let's say, geothermal and decarbonisation opportunities that we have with our very great and diverse geology that we have, and hydrogeology that we have in the UK. So I will leave it there. I've been going for nearly an hour. Bridget, shall I stop sharing? Or
I'm not sure Bridget is back, David.
okay, Victoria, you could take over.
Pulled away, but that's fine. But yeah, that was really fascinating. I think I didn't appreciate how much of a geothermal playground Cardiff was for you guys in terms of the experiments that you can get up to. Particularly like the we knew the boreholes would be too close. We thought it would be fun to find out more about that. That's brilliant.
Yeah, fortunately the NRW were I think they granted us an exemption on that one because it had never been done before. No one's been using the aquifer for heating at all or cooling. So it was very much an exploratory project just to prove whether it was sort of technically feasible or not.
Yeah,
you know, we knew it would be, but it's like, how hard can you push a thin aquifer really? It is quite a thin aquifer really. Also, I've been doing a bit of work on the chalk in Colchester with on that big open loop scheme, and that would be a really interesting one to get a talk on in the future once that's built and working and everything as well, if you're interested in that, because I know you've got lots of examples from London as well, so I'd like to hear more about what's going on in London at some point.
Just for everyone else on the call, if you've got questions, put them in the chat and we will get through to them. I see Ivan's already posted one. He says, is it true that too many closed space systems can lead to ground freezing?
Yes. I've stopped sharing my screen now. I'm just having a look in oh, you can see the chat, but I don't think I can. So yeah, you're going to read out the questions. Yeah?
I can do that.
Ivan, yes. So what you do hear horror stories of ground freezing, particularly with shallow loop systems where you can lay pipes in trenches, shallow trenches 1.5 meters deep, and you can basically lay these pipes in these trenches, and you might need like 100 meter, 200 meter long trench in a wiggly shape, and you can do it in a sort of concertina shape. That's basically a ground heat exchanger that's interacting with the soil. Now, if a building is demanding, so that's called a horizontal closed loop geothermal system, as opposed to a borehole system where you might drill 200 meters and drop the same length loop, but down a borehole rather than just around, you know, in a trench on a football field. What happens there sometimes is if it hasn't been designed correctly for the heat load of the building, if the building is demanding more heat than the ground can give it, given that the length of pipe and the heat extraction rate that the ground can supply, yes, it could freeze because the water circulating in the pipes, it's called brine, and how a heat pump works is it circulates cold water or cold fluid, and then it's colder than the ground temperature, and then the heat from the ground therefore transfers into that fluid, and that heat is transferred back to the heat pump where the heat pump does its thing. Now you can imagine if the ground cools down, the fluid in that heat pump gets colder and colder and colder it has to try and maintain a temperature difference, otherwise it can't drag heat out of the ground. And so you get a situation where and the brine's got glycol mix, so it can get down to like -3, -5 degrees and still flow like a fluid. It's like like a de-icer in it. So the ground can freeze. So basically it shouldn't happen. It happens when people don't design things correctly. It could happen with a borehole, but it'd be very hard to know if it had happened because no one monitors them. So we're quite interested in that, but generally it won't happen with good design, but it can happen. It has happened, but I don't think it happens that often. It's probably more of a kind of horror story, really.
Yeah, I think I heard about it where, as you say, the buried pipe systems from sort of adjacent gardens, and it was suggested that this could be a problem.
If they were very close, I mean, if they were more than a couple of meters apart, it might. but typically with boreholes, they space them between 5 to 10 meters apart for heat extraction purposes. And that seems to be, you can model, of course you can do the thermal modeling and everything to prove it, but that seems to be the kind of rule of thumb that as long as, with a borehole, certainly as long as it's 10 meters apart, it shouldn't really interact. This is without groundwater flow taken into account, which is a different ballgame. It will interact if there's groundwater advection, but in terms of just conduction in a non-permeable kind of strata, then yeah, as long as it's like 10 meters away, it should be all right. But it's, it could be a worry if there's other infrastructure underneath it or nearby it that could get damaged. So it really shouldn't happen even if people are designing things properly.
Speaking of infrastructure, we've got another question that's about the sewer leakage side of things. There's a question about the leakage into aquifers from sewers. Are some hot and maybe from industry sewers exploitable on a heat pump side of things?
Yeah. So yeah, good point. Great idea. So yes, sewers, apparently sewers run at about 16 degrees C all year round, funnily enough. And I'm sure we can all imagine why. And in fact, we tried to put some temperature sensors in the sewers in Cardiff, and Welshwater wouldn't let us because they're worried about fatbergs and us creating fatbergs with our little dippers. But so it's actually quite hard to get sewer temperature data. But yeah, there are some companies out there. There's one from France that I know of where they're designing. Well, you could lay these heat transfer pipes in sewers and do it that way. You could extract heat from sewers. There's another way where you can there's almost like a blanket. It's a bit like a heated blanket, the type you get on a bed. If you stay at your friend's house and it's really posh, they might have electric blankets on the beds, So, it's a bit like that. You lay a blanket in the bottom of the sewer and then these sort of pipes run through it, and then you can run this a glycol mix or maybe just even water as a transfer fluid to pick up some of the heat from the sewer. And I think there are some projects looking at that. I don't know if there's anyone actually doing that in the UK. I think they are doing it in France. So yeah, it's well worth considering doing that, and maybe even sort of replacing sewers in a way that has an easier way to transfer the heat in the future. But there is some leakage into the aquifer. Well, probably in Cardiff, because there's a couple of things. We're monitoring the water quality, of course. I mean, no one's using that aquifer. It's very shallow. It's quite contaminated in places from ex-industrial uses, probably. And the sewers, the Victorian sewers in Cardiff, many of them, and they are being upgraded bit by bit, but a lot of them, are missing bricks. So as well as sort of emptying out into the aquifer, they will take in water as well when the groundwater table is high enough. And yeah, so we actually, when we built our groundwater model, we did get the sewer network from Welshwater, and we were able to account for sewer leakage in the groundwater model, and suddenly the groundwater model balanced when you added sewers in. So yeah, kind of interesting. Good question.
I think the other question we've got on the chat is, can you explain more about the pros and cons of closed and open loop systems, please?
Yeah, sure. So pros and cons. So the let's start with the pros. So closed loop systems are easier to install because you just drill a hole and whack some pipes in the ground and grout it up pretty much. You don't have to worry about the hydrogeology too much as long as you don't have artesian water and your borehole stays open for long enough to grout it up. So installers like closed loop because of those reasons. They can get in and out. So, but you have to drill a lot more boreholes to get the equivalent amount of heat as an open loop scheme. So, for one, you probably have to drill like 10 times more borehole length to get the same amount of heat from a closed loop system as an open loop system, because groundwater is, you know, has such good specific heat capacity, and it's a really good heat transfer, and there's loads of heat in the water, so it's a really efficient way to take heat out. The cons perhaps of open loops are, so yeah, open loops are very efficient. We've shown in Cardiff that they are the coefficient, the seasonal coefficient of performance, which is a way of saying how energy efficient the system was around 4.5 at least from that open loop scheme. So whereas you might expect sort of 3.2 COP of 3.2 from a typical well-installed closed loop system, or a 2.5 or something like that for an air source heat pump. So I would say open loops are the most efficient way of doing it, but life's not all about efficiency, is it? So cost with closed open loop systems, of course, you need an abstraction license if you're abstracting more than a certain amount meters cubed per day. So yeah, you need a section 32 from the EA or NRW. It's similar in Scotland, but slightly different rules for how much you can abstract before you need a license. And then if you want to inject back into the aquifer, like we're doing in Cardiff, you also need a discharge consent or an exemption to discharge. So that obviously getting all that paperwork done, it has a cost to it, which adds to the cost of a project, which is really why you'd only, at the moment, for smaller schemes, people would be put off by that paperwork, and they'd only really bother if it was a larger heat open loop scheme where you've got 200 up to maybe 200 kilowatts that can be provided for heating a building, or up to 2 megawatts or something. So and of course an open loop as well, you need to employ a hydrogeologist, which are of course worth more than their weight in gold. And yeah, because you need a bit more specialist input for open loop schemes to make sure that the wells are designed correctly and the yields are going to be there. You might need to do, you'd probably want to do some pumping tests for a larger scheme to ensure you're going to get the yields you're expecting, so you can be sure you're going to be able to supply the heat that the customer will be demanding. Yeah, so it's horses for courses, of course, depending on what geology you've got. The costs are probably similar in the end. I think open loop schemes are probably cheaper than closed loop schemes for the same amount of heat that you're going to get out. But as I say, they're a bit more hassle perhaps for a project manager because of these slightly more complex issues around regulation and stuff. But yeah, there's another question though.
Good. Yeah, I think this is going to be the last one. Would it be feasible to use Cardiff Bay Lagoon itself as a heat source? All that water.
Absolutely. I mean, so we're monitoring the water temperatures in the river and the lagoon. In the summer, the river gets quite hot. I mean, you see kids jumping in it all the time. I'm not sure I'd want to swim in it, but and it gets down to sort of 6 degrees in the winters, and maybe colder some days when the snow's melting up in the South Wales coalfield valleys, and it's all running down the Taff River and out to the sea. So when you need the heat, it's perhaps not as warm as the groundwater. The groundwater's like buffered and it's constantly around 13 degrees C, whereas the bay temperature will be going up and down a bit. I guess at depth it will be colder as well, but you absolutely could use the bay water as in a way using an open loop, what we call open water heat pump, because you could also use the river directly, or lakes, or even some of the docks, the filled up docks and canals that are in Cardiff, Bristol and London and other places. So yeah, I mean in Norway they use fjords at Drammen to produce like 2 megawatts of heat, which is quite a lot. Yeah, so absolutely they could be doing that, and it's something that's been sort of suggested, but no one's doing it yet. Maybe with the price of gas, they'll start looking at it again. That's a good question there, Andy.
Well, thank you very much, David. What I'd like to ask everyone to do is, if they can, unmute their mics and give a little round of applause, because I think it was an excellent talk and I hope everyone enjoyed it.
very much for you.
Very much, David.
You're very welcome. Thanks for having me, everyone, and stay safe.
Yeah, it was a
And if
pleasure
you
to
have,
have you.
yeah, if you have any more questions, you can email me or get through to me via Victoria or Bridget or Mike. So yeah, I hope you learned something about the geology of Cardiff, and it would be really, oh, I see Melinda's in the room as well. Hi, Millie. Thanks for your input too. So yeah, hopefully if you're ever doing a talk about London geothermal, I'd be really, really interested to hear it.
We'll see if we can get one lined up soon.
Yeah, and I think it's worth noting, isn't it, Victoria, that there's a consultation out at the moment on the future regulation of water and heat.
Yeah.
So if people have opinions about regulation stuff, now's the time. I think Millie alerted it to me earlier today. Now's the time to shout. And
yep, absolutely.
Yeah.
Talking about talks, we're hoping for next month, if we have any entries, and we're really hoping we do, to be hosting our early careers geologist competition on the 17th. So if anybody knows any keen budding young careers geologists out there that may want to talk about something that they're very passionate about and win a cash prize and a shiny shield, let them know. That'd be brilliant. So we're hoping to host that on the 17th of November. So keep your eyes peeled. And thank you once again, David. And we'll draw that to a close. Thank you very much, everyone.
Thanks all.
Bye.
Bye.
Thank you very much.